Uh-huh.
Sorry, I actually do have one question.
Sure.
So for number 20, the equation wasn't like fully balanced. So
Number 20, the equation wasn't balanced?
Yeah.
You have to balance it. If it wasn't balanced, then it could be a mistake on my part.
From the key to the exam.
Oh, the key to the exam?
Or like it was balanced in the key, like originally.
Okay. On the quiz it wasn't. It was probably because I made a mistake on the quiz, and so I had to correct it. That's a corrected key. Yeah, it has to be, always has to be balanced. It doesn't have to. It doesn't have to be the full formulas. It could be net ionic, but it's still got to be balanced. Okay. And so the key should have been corrected. I'd like to do thermodynamics and kinetics together because why? Why do I want to do thermodynamics and kinetics together? They're really two separate topics. You know, thermodynamics deals with what? At least thermodynamics part 2 deals with what? You know, second law of thermodynamics. It deals with, when we did in Chem 1A, dealt with heat, you know, a lot of heat type calculations. In Chem 1B, when we look at thermodynamics, we're mainly looking at what? Free energy. And free energy is going to tell us what? The driving force. You know, which direction the reaction should go and how much driving force. Although some people don't like the term driving force, I like it myself. Driving force towards equilibrium, say. Not that the reaction is going to go to completion, you know, it's just going to get to where the equilibrium is predicted. We also like to look at the kinetics. And the kinetics, this is not part of the second law of thermodynamics. You know, this is a different question. Normally, if something has a big driving force, you know, you expect it to be a fast reaction, and that's typically the case, but not always. And so these are two separate topics. And so we're going to look at kinetics, the speed of the reaction, and we're still going through the empirical versus the theoretical. What's the difference between empirical and theoretical?
Empirical is based on experiment?
Yeah, observation, based on observations. And they, like in physics, they divide the physics community into the theoretical physicists and the experimental physicists. The experimental physicists are empirical. They're looking at the empirical data, you know, from observation. And the factual observations always end up winning any argument when it comes to theory versus observations. So we're looking at this like this. This is a pretty rapid reaction generating lots of energy. The energy, you know, can be in the form of heat, it can be in the form of light, it can be in the form of sound, it could be mechanical, it could break things, you know. And so lots of energy. This is highly exothermic, and you can see that. But it's not quite explosive. Explosive reactions, this could potentially be explosive. You know, explosive reactions happen very quickly under certain conditions. You know, the combustion of flour, you know, you don't think that of that being very explosive, but there have been lots of bakery explosions where they generate a dust cloud of flour or sugar and flour, and that ends up igniting in just the right mixture in air and causing a violent explosion. And grain silo explosions too, you know, just under the right conditions, a reaction could be quite explosive. The same thing with methane. And so this is interesting because this is ammonium dichromate. This is called the volcano reaction. It's a redox reaction. Usually you got to watch out for reactions that generate gas. Reactions that are highly exothermic and generate gas can be quite explosive here. And so nitrogen gas, but only 1 mole. Some like ammonium nitrate generate a lot more gas. But this is ammonium, what's this one? CR207?
Dichromate?
Dichromate. Dichromate is a pretty good what? If you think about it, yeah, it's a pretty good oxidizer. +6, chromium 6 is a good oxidizer. And ammonium is a good reducer. This is a potentially unstable compound because you have ammonium and dichromate. Ammonium is a good reducer, dichromate's a good oxidizer. They're both in the same compound. And so it's potentially dangerous. What prevents these from reacting? What prevents these from reacting is they're in their lattice position. And in order for them to react, we need a collision, a more violent collision between the ammonium ions and the dichromate ions. At room temperature, the vibrations aren't violent enough. What you have to do is you have to heat this up, right? As you heat this up, then the vibrations will become more intense, and eventually there could be a collision, and that collision can result in reaction. So this is what happens. You just heat it up. You get a little torch or a heat gun or something, and just get the vibrations going. And once that happens, then the volcano takes off, and this is a pretty mild reaction. You know, it just goes. It just creates a huge mess. Chromium. It's to clean up. And so this is a popular demo. But what we're going to look at is we're just going to look at first just measuring types of reactions. I'm not going in exact order of this. And then we're looking at the theoretical models for chemical kinetics. So just continuing on where we left off in the video here. Hopefully this is not going to... Actually, I thought... Okay, now it's working again. Yeah, can you tell this is a second order decay? How can you tell that this is a second order decay? I had it labeled as first order, then I looked at it. This is definitely not a first order decay. Yeah, originally I had the exam scheduled for tomorrow. If you guys are ready for tomorrow, I'll give it to you tomorrow. But if not, then I'll just give it Monday, so we have some more time.
How many more chapters do we have?
We have kinetics, then we have electrochem, which is redox, and then we have the last part of chapter 24, and then a survey of nuclear chem. And so like 3.5 chapters, including this one. So the electrochem is, since I already talked about redox, it will go by pretty fast. But so we have 3 weeks left, right? 3-4 weeks.
Do you know how many chapters would you fit in?
Well, the thing is, I can't give you a test on each individual chapter, so what I do is I just roll those questions into the final. So normally I put the electrochem on the final, but what it ends up happening is it's not like a 2-part final, like the last part of the class and then everything else. It's just blended. So what ends up happening is, let's say on the final exam I have usually like 60 questions, multiple, or 100 multiple choice questions or something like that. And what that means is you'll have a few extra multiple choice questions from chapter like 20, electrochem, chapter 24, and maybe some nuclear chem questions. Nuclear chem I usually cover just in one day.
Are we gonna do a 2-part final like we did last semester?
We're going to do a 2-part final because we have to come back on Monday. So the 2-part final is Thursdays. It's kind of weird. I don't know why they did this, but they have on Friday's graduation. I have to go through the graduation ceremony, and then Monday's our last day of class. Monday's a 3-hour class. So what I was thinking is on the Thursday it's an hour and a half, so we'll have some free response type questions on that day. And then on Monday, And some people ask, they want to take it early. That's possible. If you don't want to stick around the following week, you can do the multiple choice part 2. But I'll be here. It's going to be a 2-part final.
When would you take the second part, right? Be on that Thursday?
Yeah, I'm probably on the Wednesday because the Thursday, I don't know if you can finish it. If you can finish it in 2 hours, then you can take it on Thursday if you want. I mean, you'd have to do the free response and that. So you'd either stay for the afternoon, or for the afternoon they'd have to come in the morning, basically.
For the past exam, did you like
Oh, I'll give you the past exam tomorrow. Give that. They have to finish it.
The formal report, can I have that?
The formal report, yeah, we're going to do that. We're going to do that together. Formal report. We'll just start that tomorrow. Formal report. We're going to do a lab. If we're not taking the test tomorrow, we're going to do a lab. It has the last part of chapter 19 in there. The section I didn't cover. We're going to deal with it in the lab. And then we'll start writing the report. Reports. Did you have to do a formal report in Chem 1A?
No.
No? Well,
I mean, I
oh yeah, we did. But other people?
Not before.
No? All right. I'll just figure out. Like at UCLA, I worked as a grader there, and every single report was a formal report. After a while, it becomes easier. Initially it's kind of a pain because you got to figure out the style, the format. You just make sure everything's. So we'll just do those. But getting back to this, originally I had this marked as first order. Then I looked at it more carefully. This can't be first order. Why?
The concentration is taking double time.
Yeah, double time here. This is like double time. If it were first order, what would happen with the time?
Half,
Yeah, it would be, the time would be fixed, it'd be constant. And so that curve is a second order decay. So that's not quite right. So let's draw the first order decay curve. And so I'll do that here. There's not much room, but let me try that. So when we do concentration versus time for first order, we start off with time 0, the initial concentration here, and then we'll cut that in half. This is about halfway, and then it's going to take some time, which we call T1/2, time it takes for 1/2 of the concentration to disappear. Okay, now this is our new time 0. And so the book has different ways they name this, so it depends. A lot of times we assume that the initial time is T0, but sometimes we reset that, and so this is a new initial time. If we reset that, then I would change the formatting of some of the equations in the book, but I'm not going to change it. T is just an interval. T is really our delta T, and so it depends. It doesn't matter where we start. It's the time interval here. So if this is our new initial, we cut that in half. For first order, how long will it take for it? And so if we cut this now in half, so let's say we're here, how long is that going to take for first order?
Sorry, I was just wondering, isn't next Monday Memorial Day?
Oh, that's right. Next Monday is Memorial Day. It's a 3-day weekend. We can move it to Wednesday then if you want.
Is it possible to take it this Thursday?
It's possible to take it Thursday. We could take it Thursday. I might make it shorter. I don't know. Do you want to take it Thursday?
Or Wednesday?
or Tuesday, if I make a shorter test. No, Wednesday? All right. I think the consensus is going to be next week then. Were you prepared, Alexa?
Oh,
For
it's just like I'm worried about condensing.
condensing the rest of the stuff? All right. Well, the other stuff's going to fold into the final. So don't worry about it too much. Right?
Okay.
All right, so here we have this. It's going to take the same amount of time. So then I know this is first order. This is second order because the half-lives grow. And so how long would the next half-life in second order be? In second order, the next half-life is going to be double the previous half-life. So if it was this long, then we got to double it. And that's how long it's going to take. And so this one, the next half-life is going to end out here. Do you see that? And so this is a very slow decay compared to first order. First order is a much more rapid decay because the next half-life is the same here in terms of distance here. And then the next half-life is going to be the same here. Each successive half-life is the same. It's going to take infinitely long. You know, both of these are going to take infinitely long to have 100% reaction, right? And so we don't, complete reaction for these is like 99% reaction because we don't want to wait forever for 100% reaction, right? However, for zero order, let's see, did I do that? So here the curve is, we could easily recognize it based on the curve. This curve is a first order decay here. There. This curve we can recognize as a second order decay, and the other curve you got to recognize is a linear decay. This was supposed to be a linear decay, but this one we don't have to wait forever. This point is off, but it's okay. The other points kind of make this line, and this was supposed to be a straight line here. This one is going to hit zero here, 100% reaction at this time. Each half-life is half as long. Each half-life is half as long. And so those are the three that you should know. You should know these three curves. The linear, the first order, the first order we call exponential decay. This is exponential. Okay, and then the second order. So let me write that here. This is first order or exponential decay. Uh-huh. Are there like an infinite, not infinite, but more than what we're covering? And the problem is for example, you could have fractional orders, like you could have 0.5, you could have negative orders. Negative orders is like negative feedback. And so if you have a negative order, what that means is as the concentration grows, let's say the concentration of the reactant grows, the reaction rather than speeds up, slows down, or as the concentration decreases, it speeds up. It's more complex, and so we have to figure out why. Well, the first question is, where do these orders come from? But this is just recognizing. So the reaction could be what we say second order overall. If the reaction is second order overall, it's going to have a decay like this, or if the reaction is first order overall, it has a reaction curve that looks like that, or if a reaction is zero order overall, it has a curve like this. All right. Oh, shoot. I lost my additional notes from this, unfortunately. Gosh. So, did I write? what we're going to do is we're going to simplify these into just these type of reactions. This type of reaction is just we only have one reactant going to product. Well, there's a very limited number of reactions like that. For example, the volcanoes like this. The volcanoes like this because we only have one reactant, ammonium dichromate. The ammonium dichromate decomposes, forms a volcano. Hydrogen peroxide is like this too. But most reactions aren't like this. Most reactions have more than one reactant. And so I wanted to make this point here just to emphasize this. So most reactions have more than one reactant. And so what we're doing here is we're just going to limit the scope of our studies. So again, for reactions of this type here, where we have multiple reactants, the only thing we're going to get is the rate law. No integrated rate law. We could do the integrated rate law, but it's just more advanced calculus. So the only types of questions that we can ask when we have this is, what is the rate law? The rate law is going to be Ka to the M, B to the N, C to the O, etc., however many you have in there. Once we figure out what M, N, O, and K are, then we can predict the rate at any concentration. And so we can say, what if the concentration of A were this, the concentration of B were that, and the concentration of C? How fast would the reaction be going at that point in time? Because as soon as you go past that, as soon as the concentrations change, then the rate changes again. And so the rate is continually changing, so we're just going to pinpoint the rate at certain periods of time. Now, M, N, and N can be more complicated. You know, you could have negative M's, fractional M's, etc. But what we're going to see is the overall order of reaction. The overall order of reaction is equal to the sum of these, M plus N plus O plus etc. So if you have a first order overall, let's say M were 2 and N was -1, then it would be first order overall. Then we'd have that first order curve. But the actual kinetics of the reaction is kind of complicated because it's second order in A and first order, negative first order in B. So, you know, we could have a much more complex thing going on here. But what we're going to see is the overall order. That's what's going to dictate the curve that we see here. And those are the curves up there. But, you know, what we want to do with these curves is how long. Like, for example, if we say, okay, I'm just going to wait until 99% of the reactions occurred. If I wait until 99% of the reactions occurred, how long is that going to take? You know, for second order, 99% of reaction is going to take kind of a long time, you know. Like, how many half-lives would that take, or how long would that take? Well, how many half-lives, that's too complicated here, so we wouldn't think about that. But certain processes with first order, we might think in terms of half-life. How many half-lives would it take for 99% of the reaction to occur? Well, it so happens that, like, nuclear decay is another one that we could do simply, like AA goes to product. you have some radioactive isotope. We want to know how long will it take for 99% of that radioactive isotope to decay. Do you know approximately how long it takes for 99%? About 5 half-lives. We could just figure it out here. The way people figure it out is, the first half-life, we're down to 50%. That means 50% reaction, 50% left over. The second half-life, we have how much percent reaction? At the second half-life, we have 75% reaction, 25% left over. At the third half-life, we'll have 87.5% reaction, 12.5% left over, et cetera. You can kind of figure it out that way. In fact, that's the way people do it for multiple choice questions when they're asking. This is for nuclear chem. Nuclear chem, sometimes they don't just worry about 95% reaction. How much does it take 95% to decay? Or something, or 99%. So some people will say, okay, after 5 half-lives, the uranium's dead, kind of thing, because there's so little left over. Let's say less than 1%. But it's not really dead. I mean, it's still going to take forever. But the problem with the uranium is, you know how long the half-lives are? Depends on which isotope of uranium, but some of them are like 4.5 billion years or so. So 5 half-lives would be a long time to wait. Whereas things like radioactive iodine, I think radioactive iodine has a half-life of 5 days, so up to like 25 days. But then there's a couple of things, like for radiation exposure, if you have iodine, there's a biological half-life. Depends on where it gets incorporated. Like if it gets incorporated into your thyroid, then the biological half-life is a lot shorter than if it gets incorporated into your bone, like calcium, that kind of stuff. So half-lives are important in a lot of kinetics. And so the biological half-life is, the biologists talk about biological half-lives all the time. Certain things get into the body. Okay. So half-life analysis is useful. All right, so if we have a more complex reaction and we figure out the rate law is usually, the easiest way to determine the rate law is to use the method of initial rates. That is, you double the A concentration, see what happens. If you double the A concentration and everything stays the same, then M's 0. You only have 3 choices, because that's what we're going to limit it to, 3 choices. If you double the A concentration, actually, there could be more. We could be more complex here. If you double the A concentration and the rate doubles, then it's first order. Or if you double the A concentration and the rate quadruples, then M's got to be 2, because if you get a square, 2 squared will quadruple the rate. And so that's the method of initial rates. It's straightforward. Okay, now if we want to do anything more complex, we're really limited. We don't want to spend too much time with the math. And so we're only going to look at very simple decomposition reactions of the sort AA goes to product. And we need to figure out the rate law. Well, the rate law is going to be a lot simpler, so we have more choices. We could use the method of initial rates here. Be the same thing. We double the A concentration, see what happens. If it stays the same, it's 0 order. If we double it and it rate doubles, it's first order. If we double it and it quadruples, second order. And so when we do this, we're going to limit the type of reactions that we see to 0, first, and second order. Reactions only. Limit scope. So we aren't going to get all fancy and try to do a bunch of stuff. And so what are the ways? Well, it turns out there are more ways to determine the rate law than up there. And so the rate law is just this. We have the rate constant k, and this is going to equal a to the n. And so here we could use the method of initial rates to determine the rate law. Method of initial rates. Or we could do what we call the graphical analysis. If you have Excel, you can do this very rapidly. For graphical analysis, we just graph it. A graph of concentration versus time comes out linear if zero order. If this is linear, then it's zero order. If it's nonlinear, then it's either first or second order. But the problem is this. Problem is some people don't want to wait so long to collect the data. So for example, they just collect the data at the very beginning and say, okay, that's enough data. So sometimes what you see is if it's clear, if it's easy to see, then and we have lots of data, then no problem. We can see. For example, you can easily recognize this decay. Can you tell me what this is? Oops. Is that first or second order? That's first order. Not a very good drawing of it, but it's first order because cut in half, cut in half. Do you see that? The problem is that some people don't want to collect that much data, or they just collect, the reaction might be slow too. So the problem comes up is if they only have the first, let's say, the first section of this. If we have the whole graph, no problem. We can see it and eyeball it and then just tell directly. Because you only have three choices, 0, first, and second for this type of reaction. And so this is the problem, though. The problem is if the graph, the entire graph, just consists of these points right here near the beginning. Let's say they collect a whole bunch of data here. Can you tell what this is? Is there enough data to easily distinguish if that's first or second? No, there isn't enough data because we cut it in half, but we want to cut it in half again, but there's no data. Do you see that? So if there's not enough data, how do we know? So not enough data to see. Not enough, well, not long enough to see here because we just cut it here. This is the end of the experiment and this is the only curve we got. That's it. So if you can't just see it directly, if you can see it directly, then easy. We don't have to do any math. So if I have the curves like in the black here, then no problem. Eyeball it, that's enough. If I have a curve like in the red here, then we need more data or we need math to figure it out. Not long enough to see the full curve. So in our graphical analysis, this is what we do. And probably with Excel, you just automatically do this. This is plot 1. And then we make plot 2. Plot 2 is we'll take the natural log of the concentration versus T. And if the natural log of the concentration comes out linear, then it's first order. Because 0 order would give a natural log plot that's nonlinear, and second order would do the same thing. It would give you a nonlinear log plot. And then finally, we'll do plot 3. Plot 3 is, what we'll do is we'll just take 1 over A, or 1 over the concentration versus time. And this is going to come out positive slope like this. And if this were linear, then we say it's second order. And so graphical analysis we could do quickly with Excel. We'll just make 3 plots, see which one's the most linear. The most linear one will give you a linear trend line with an r squared. We're looking for an r squared value in the high 9s. R squared would be the correlation to the fit for a linear equation. Okay, the next thing is this. Are you going to have Excel on the exam? No. You're not going to have Excel on the exam. And so the next type of analysis, which I'm going to call is K-analysis. So let me give you an example of this. And then the fourth one would be a hybrid method. The hybrid method would be, for example, what we're going to do in the kinetics lab. In the kinetics lab, we're going to do a combination of method of initial rates and graphical analysis. The reason is to do the method of initial rates properly, we need 3 trials. We only took 2 trials. The reason we can eliminate 1 trial is because we're going to use graphical analysis to figure out one of the variables, m or n, and then the method of initial rates to figure out the other variable. So it's a hybrid of these 2. For our K-analysis, let's see if we can eyeball what we can eyeball for order based on the data that's given. And so take a look at the exercises here. The exercises. So here's just some delta y over delta x, you know. Here's a method of initial rates. Some of these we could just see right off, you know. Don't really need a mathematical equation. A's kept the same, B's doubled. We doubled B, what happened to the rate? Well, this went from 3, 10 to the minus 4, so this goes from 3 to 13, so it quadrupled. Do you see that? The rate quadrupled, that means it's second order in B. And then we look, okay, here A's the same, and B doubled. Well, that's what we had up there. We need to double A. Here we double A, but B changes. I don't want B to change. Here we double A and B stays the same. So between 2 and 4. Do you see that? So here we double A and what happened to the rate? Went from 13.5 to, we doubled the rate. So it's first order in B. So first order in A, so M is 1, and second order in B, N is 2. And the only other thing we need is k. The way we calculate k is each of these will give us a k value. And so we just solve the equation for k. K is equal to a to the first, b to the second, divided by the rate. And so we just plug in the concentrations, square this one, and then divide it by the rate. Each of these k's should be the same, because k is a constant for the given reaction. And so we calculate 4 different k's and then just average them. That gives us our best k. There's going to be some fluctuation, so the best k is the average, rather than just calculating one of these. So just more method of initial rates. So for method of initial rates, we got to do a lot of experiments here. And it's just the initial concentration, because as initial concentration changes, so does the rate. And so at least we know what everything is right at the beginning. All right, here's some data. Let's see if we could figure out what order this is, just based on the data table. So I start off at 1 molar. Well, that's kind of convenient. And then I want to drop it down to about half. And so half is around here. And then we take a look at how long. It took between 50 and 75 seconds, correct? And so we're about 0.5, and then we want to go to about 0.25. And so how long did that take? About another 50 to 75 seconds. So what does that tell you? That tells me that this is first order. So I could just look at the data table and see this is first order, right? We go from 25 roughly to about half of 25, around 12. How long did that take? It took about another 100. Or did that take 100? No. Oh, no, to 25 to about here, so 50 to 75 maybe. It's a little bit tricky because these aren't exact, but this is first order. How about this one here? What order is this one? Oh, this is easier. 1 to 0.5 took 50 seconds. 0.25 took 25 seconds. Oh, it's done. What is this? This is zero order. I mean, you only have 3 choices. You just memorize them. And this is zero order. These are two separate reactions. These aren't the same reactions. So I don't know why they didn't make 2 separate tables, because these 2 are totally different reactions. But they're still the same A. So they just use A for everything, because there aren't that many reactions, right? That, like the dichromate or whatever. But that's a pure solid. Well, let's take a look at this data table. 1 to about 0.5 took 100 seconds. And then 0.5 to 0.25 took, well, it's looking like it's taking longer. Since we're limiting the scope, you only have 3 choices, so this must be second order. The problem comes up with something like this. We're starting out at 1.512, and the last piece of data they collected is 1.469. Can you tell me what order this is? No. We can't, because this is too hard to eyeball, right? In fact, if we plot this out, can you tell me what it is? No, because it's just that first little bit of data here, right? So one choice is method of initial rates. So to get the initial rate, there are 2 ways we can get the initial rate. What are the 2 ways we can get the initial rate? The first way is we draw the curve and then draw a tangent line at time 0 and then measure the slope of the tangent. That gives you initial rate for experiment 1. Or alternatively, we take the average slope if less than 5% reactions occurred. Has less than 5% reaction occurred? Yeah. And so what we can do is we can just take the slope of this, just pick 2 points here. I'd pick the first 2 points because that would be closer to the initial rate. And I'd figure out the average rate over this time interval from 0 to 1 minute and call that the initial rate, because drawing the tangent line is a pain at time 0. And so most likely I just ignore this point, do this and get the rate. And so this would be the rate with A0 at 1512. Then how many more experiments do I need? I need one more experiment, right? I'd like to double that and see what happens, but I don't, because in the second experiment, or is it doubled? It is doubled. So they doubled it, and then they look at the rate, you know. And so here, less than 5% reactions occur. Take these 2 points, get the average, do the slope. That's one way we could do it. We can just get the rate from there, the initial rate. This is why they didn't collect that much data, because all they care about is the initial rate. They don't care about the rate way down here, right? Just the rate at the very beginning. But you know what? I wouldn't do it this way. I might. You know, because calculating the slope of this is not that difficult. In fact, let's do a quick calculation of the slope and see. Because if the slope stays the same, what order is it?
0.
It's 0. If the slope, actually, if the slope, let's say, doubles, so we doubled the initial concentration, we went from 1512 to 3024, and if the slope doubles, then we double the concentration, the slope doubles, it's first order. Or if we double the concentration and the slope quadruples, it's got to be, we only have 3 choices, so it's not difficult to figure out. And so we'll take our delta y and our delta x, and the slope is, even though this is negative, we're going to make it a positive by either taking the absolute value or multiplying by negative or whatever. And so I'm just going to subtract it in reverse order. 1512 minus 1.49 equals, and that's in 1 minute intervals, so that's easy. So 11/500ths, 0.022. Remember 0.022, that's the initial rate for this one. Okay, then I'll do the same thing here. 3.024 minus 2.935, 0.089. So 0.089 divided by 0.022, 4.045. 4.045 means it's second order. Got that? And then we have the concentration, we have the rate now. We can figure out K. We can figure out K from run 1 and K from run 2. Okay, that's option 1. Option 2. We make a graph. We make a graph of these, you know, in Excel. Is that okay for option 1? You know, just verbally. I didn't write anything down, but did you get it? Pretty much? I mean, were you able to follow along? Or should I write some stuff down? Mm-hmm.
Sorry, can you go over the calculation?
All right.
Just like which numbers you
All right, which numbers I did? All right, this is, of course, is more complex because we don't have enough of the graph. So this is like being in the red zone here. We're in the red zone here. So the first method we're going to use is method of initial rates. And the first thing we need to do is determine the initial rate. So the initial rate is equal to the slope of the tangent line at t0. Number one, I don't want to graph this. Number two, I don't want to draw the tangent line. So I'm not going to do this. I'm just going to say, or approximately equal to the average slope when less than 5% reaction has occurred. So the average slope of the very beginning of the reaction. Average slope of the very beginning of the reaction and the criteria for what is the very beginning of the reaction is less than 5% reaction has occurred. So by the time you hit the first data point, let's say 20% reaction has occurred, it's too late. You know? If you hit the first data point and less than 5% reaction has occurred, then we're good. And so has less than 5% reaction occurred here? So let's see what it is. Well, looking at it, it looks like it, but let's see what the percent reaction here is. So the percent reaction here is, I'm just going to do it like this. I started off with 1.512 initial minus 1.490 divided by the initial amount, 1.512, times 100. That's going to give me my percent reaction. So 1.512 minus 1.49 divided by 1.512 times 100. And that gives me 1.45% reactions occurred here. Oh, come on. What happened to it? There it is. Now, the situation is this. We are always dealing with random error. And so when we do calculations, we try to use all the data that we have. And so normally I would try to use all this data to try to kind of figure it out. Maybe I'd try to assume it's linear right at the very beginning. You know, because if you look at a curve and you focus on a tiny part of the curve, it kind of looks linear, right? With the tiny. But the other issue is that if this were, let's say, a first or second order, then the rate's changing with time. So the rate's already changed here. So on the one hand, I want to use more data. On the other hand, I don't want to wait too long because the slope is changing. So I'm only going to use these first 2 points, but the risk there is random error. You know, that random error could have thrown that off. You know? But it's all right. We're just going to do it this way. I mean, there's a trade-off in doing it either way. You know, just plotting all three versus plotting these two. Well, if I plot just the 2 points, then 2 points define a straight line, and so we can figure out the rate. And so we just calculate the slope. The negative slope of this is going to be the initial rate. Not exactly, because technically the initial rate is right at time 0. The instantaneous rate, we call it, not the average rate. And this is the average rate here over a 1 minute interval. So this slope is the average rate over a 1 minute interval. Okay, so that's delta y over delta t. And this is negative, so I need to do absolute value here because rates are always positive. And so this is delta y is y final, or the concentration final, 1.490 minus the initial 1.512. And t final, 1 minute minus t initial 0 minutes. And the units of this are going to come out in molar per minute. So it came out to 0.022, so recall 0.022. Now we're allowed, in the subtraction here, it looks like we're going to have 2 sig figs. Yeah, 22, 2 sig figs. So we're only allowed 4 decimal places, 3 decimal places. And so that's 2 sig figs, so the sig figs are right. And that's a 0 afterwards anyway. All right, we go on to experiment 2, and the first thing we ask is less than 5% reaction, because if more than 5%, then we're going to have to graph this and then take the slope of the tangent line. But let me do the calculation here. 3.024 minus 2.935 equals, divided by 3.024 times 100, 2.94% reaction. And so again, this is going to be 3.024 minus 2.935 divided by 3.024 times 100%. And I get 2.94% reaction. So we're okay. It's getting 3% reaction is getting higher. This is probably more than 5% reaction here, the next data point. But that's good enough for the initial rate. Again, we're assuming the initial rate is approximately equal to the average rate over this 1 minute, as long as less than 5% reaction. That's because we had 2.9% is less than 5%. We're okay for that. Then we figure out the rate of the reaction. The rate is going to equal delta A over delta T, an absolute value. And then the final concentration is 2.935 minus the initial concentration 3.024 divided by the final time, which is 1.0 minus the initial time, 0. That's going to be the same units, molar per minute. So 2.935 minus 3.024. 0.089. Molar per minute. And then what I'll do is I'll just take, I could do this the proper way, or I could do this the quick way. Which do you want me to do? All right. Well, I'll do it the quick way first, and then I'll do it the other way. The quick way is this. We double A. That is, we went from 1.512 to 3.024. We double A, what happened to the rate? And so the rate went to 0.089. And so we started off with a rate of 0.022. That comes out to 4.045. Times faster. So when we double the A concentration, the rate went 4 times faster. We only have 3 choices for this. It's either going to stay the same, that is, the rate doesn't change, or the rate doubles, or the rate quadruples. So this is quadrupling, therefore it's what order? Second order. All right, and then the proper way to do this. I put the faster rate on the top, so I'll do rate 2 over rate 1 is equal to, the rate 2 is equal to K, concentration, initial concentration for rate 2. So I'll call this, let's say, A02, comma 2 to the M over K A0 1 to the M. then substitute this in. Rate 2 was 0.089. The units will cancel. And rate 1 was 0.022. And the K's cancel also, because the K's are going to be the same for each. And so this is going to be the concentration of A on 2, which was 3.024 to the M, divided by the concentration for 1, initial concentration, 1.512. The units will cancel to the M. This is going to equal 4.045 to the mth power. Or is that, no, sorry, I screwed that up. Let me fix that. It's not 4. 3.024 divided by 1.512 comes out to what? Exactly 2, right? 2.000. They made this easy for us to the mth. Now we have to solve this for m. So what most people do is they'll take the natural log of both sides. So we'll take the ln of this 4.045 is equal to the ln of 2 to the mth. And then they'll use the property of logs to bring this down here. And then we solve for m. M is equal to ln of 4.045 divided by ln of 2. All right. So you could use the property of logs to simplify further. I'm not. I'm just going to take the ln of 4.045, just equals, divided by ln of 2. And m comes out to 2.016. So m is close enough to 2. We just call this second order. Uh-huh.
Is the quick way like just as accurate as the proper way?
Yeah, the quick way is fine because we only have 3 choices. It's going to be 0, 1, or 2. So why bother? If we had 2.012 order, you know, is this because of random error or is this real? That is that real? Well, only 3 choices for us because we're limiting the scope. But let me give you a story about something here. The story goes like this, and I can't remember the exact ratio. Maybe I should look it up really quick. Let me see if I can find it really quick. If not, I'm pretty sure it was 1.95. Yeah, it is 1.95. So remember in Chem 1A, determining empirical formulas? An interesting thing happened. Let me tell you about this. This was, I think, at the I think this happened at the MIT Lincoln Laboratories. They have this Lincoln Laboratories there. It's like Lawrence Livermore Laboratory they have at Berkeley. But you think they can determine empirical formulas with high degree of accuracy and precision, right? So they were determining the empirical formula of this, and so, but they kept getting 1.95. And normally if you have random error should fluctuate, right? Sometimes it's high, sometimes it's low, right? But each time they were getting 1.95. That's kind of weird because, why are they getting one? It could be, it could be like, it could be like one of those things where, you flip a coin, it should come out heads or tails, right? But let's say you kept flipping the coin and every time you flip it, it comes out heads. Is that statistically possible? It's possible, yeah. I mean, that's one of the possibilities, it's heads or tails. But every time you flip it, it's coming out heads. It makes you start to wonder because you'd expect some fluctuations. It turned out that this 1.95 is real. This is what we call non-stoichiometric compound. Normally it should be MnO2. That should be manganese peroxide. It should be MnO2, not MnO. So normally we just round that off. We just call it MnO2. But, these guys are really sophisticated. These guys are saying, well, why is it coming out 1.95 every time, right? And it turned out it was real. It wasn't MnO2, it's MnO 1.95. And do you know the reason for that? The reason is because manganese wasn't plus, 3.9. It wasn't because manganese wasn't 3.9, it lost a tenth of an electron, or, less than it should have. It was because of defects. There are defects in the crystal lattice, and some of the defects had a missing oxygen. And so this is why, this was caused by defects. This turned out to be real. So when I round things, I always wonder about that. This turned out to be real because of defects. Normally, we just round that. Normally, you just round this and say, okay, it's MnO2. But MnO2 would be incorrect. It's not MnO2. And so when I have something like this, I start to worry. Is there something going on theoretically with the kinetics? Because really what we want is we want to know the we want to know the empirical, but we also want a deeper picture, and the deeper picture is going to be theory, And so when I round this from 2.012 to 2, I worry. Did I round something that was real? There's some weird stuff happening with the kinetics, or is that just random? Because in the next set of experiments, it might come out to 1.98. Who knows? Just round it to 2. For us, we don't have to worry about it because we only have 3 choices. Makes our life a lot easier. So. But it also limits the scope of things, and so we have to be careful because as you progress in science, you have to be careful about these types of things. I mean, there are people who are worried that, they're worried that things like the theory, the theory works fine and everything's going great until one day it doesn't. One day there's a piece of data that throws the whole thing into question. Right now, quantum mechanics has been very successful, but people are saying, there's got to be something more because, what's going on with dark matter, and gravity, and it's not a complete picture. And so people are worried that, it's just working until it doesn't, but maybe it just continues working. Maybe it's very solid, it just continues. Quantum mechanics has been extraordinarily successful up to this point, and so I don't foresee it, doing something like that. But here, the quick way is fine. We didn't have to do. I saved myself a couple of minutes doing this math, doing it the quick way. All right, that's a method of initial rates. The other option is we could just plot the data. Plotting the data is fast if we have Excel, which I have. I have Excel. So I'll show you how we're going to plot the data in Excel. So let me make a new plot here. And then we'll just get the two experiments here. So 1.512 to 1.49 to 1.469. Oh, I'm not done. Yeah, because, yeah, let me finish the previous problem and then I'll do this one. So m is equal to 2. We're not done. We need one more thing. And so the rate is equal to Ka to the m. So far we have Ka squared. The last thing we need to do is determine K. So what we can do is we can get from run 1, we can determine the K from run 1. And the K from run 1 should be the same as the K from run 2. So the K from run 1 is equal to the rate over A from run 1 squared. And so the rate from run 1 was 0.022. And here we keep track of the units, molar per minute, over the concentration from run 1 was 1.512 molar. And so the molar cancel out, and that gives us per minute. And so this is 0.022 divided by 1.512, which gives us 0.01455. And the units here are minutes to the minus 1. We're only allowed 2 sig figs, but I'm not going to round it yet. And then we're going to go for run 2. This is run 1. Run 2, we're going to get K2, which is, this is the rate from run 1. This is going to be the rate from run 2 divided by A for run 2 squared. And so the rate for run 2 was 0.089 molar per minute divided by the concentration, which was 3.024 molar. And so what does this give us? 0.089 divided by 3.024, which gives us 0.02943. Did I screw that up? No, I guess I get it right. 0.02943 minutes to the minus 1. I have a big problem. My big problem is that the two rates, I mean, are good, different, but the two Ks should be the same. The two Ks should be the same because it's the same reaction. And so I must have screwed something up. Oh, you know what I screwed up? Do you see what I screwed up? I forgot to do something. What did I forget to do? I forgot to square this. And that's going to change my units. Too. This is going to be molar. Minutes to the minus 1 times molar. Minutes to the minus 1 times molar. K is going to, the units for K are going to depend on molar to the minus 1. Molar to the minus 1. Because I have molar squared on the bottom and molar on the top. I forgot to square that. So I'll do that again. 0.022 divided by 1.512 squared. 0.009623. Sorry. Oh, 9623. Okay, and then 0.089 divided by 3.024 squared. .009732.5. Now they're supposed to be the same, but you can see they're slightly different here. Actually, they look kind of different. And so I don't know which one's more accurate. So what we're going to do is we're just going to take K average. And so I'll just average these two, plus 0.009623 divided by 2. 0.009677. How many sig figs? I'm only allowed 2 sig figs, so this is going to be 0.0097. I'll just say molar to the -1, minutes to the -1. So now we can determine the rate law. The rate law is just going to say the rate is equal to, delta A over delta T. Delta A over delta T, the slope is always changing, It's always changing with time. And therefore, it's going to equal this. K, which is 0.0097 molar to the -1, minutes to the -1, times the concentration of A squared. And this would be our rate law here. So this changing rate we can determine at any concentration during the course of the reaction. The next thing we want to know is how long this takes. So once we have the rate law, then what we're going to do is we're going to get the integrated rate law. And so to answer any remaining questions, we need to know, okay, this is second order, and therefore any other types of questions we get from 1 over A at time t is equal to kt plus 1 over A times 0. The k is the same as this k here. And this allows us to answer questions of how long and how much. Let's say I wanted to know if I want 95% reaction to occur, how long will it take? All right.
Does that say
KT.
KF?
So we could just do that right here. Let's say I want to know how long will it take for 90% reaction to occur. Could I use the rate law to do it? Could I use this equation to figure out how long it'll take 90% reaction to occur? No. You're not going to be able to use, unless you know calculus, you can do this. But you'd probably end up doing the same thing. So how long for 90% reaction? That means the concentration of A at time t, which is 90%, is equal to, well, I'm only going to have 10% left, so that's going to be 0.10 of my initial concentration left over. And then I'm solving for t. So if I solve that equation for t, t is going to equal 1 over A at time t minus 1 over A at time 0 divided by k. So the invert key is very nice on this. So let's say if my initial concentration, so this is going to be 1 over 0.10 or 0.1. I'll keep the track of the sig figs in my head. 0.1 A0 minus 1 over A0. Over k. I'm going to need some information here, because will the A0 factor out? And so 1 over that is going to, this is going to give me minus 1 over 0.9 A0, correct? Divided by k. Does that look right? Okay. But I don't have enough information. Do I know what A0 is? So this is what I'm going to do. I'm going to do for experiment 1, run 1, and for run 2, and see if they come out the same. So how long for 90% reaction for run 1 and 2? Do you think they're going to come out the same amount of time, or will they come out a different amount of time? You know what I'm going to say? They're going to come out a different amount of time. Why do I say that? Because I can't get rid of the A0. A0 is in my equation here. Okay, so for run 1, A0 is equal to 1.512 molar. Therefore, the time is going to be, how did I get a negative? Did I get that right? Yeah, I did get that right. Okay. That's going to be, or did I? I don't know. Let me go off this equation here. Since my calculator has an invert key, I'm just going to use this. Just make sure I didn't make an algebra mistake. So this is going to be 1 over 0.1 times A0. So 0.1 times this is going to be 0.1512 minus 1 over A0, which is going to be 1 over 1.512 divided by K. K that we just calculated is 0.097 molars to minute. Molars to the minus 1, minutes to the minus 1. In the numerator, I'm going to have molar to the minus 1. So those are going to cancel. And it's going to give me minutes to minus 1, which will give me minutes in the end. So I'm going to go 0.1512 invert minus 1.512 invert equals divided by 0.0097, 613.6 minutes, or 610 minutes. I'm out of time. And then we could see for run 2 how long it would take 90% reaction, see if they come out the same, which I don't think they're going to come out the same. All right. Yeah, sorry. I went over time.